So we were talking about the Hicksian demand and or a compensated demand, and in particular the expenditure function. And the expenditure function was how much do I have to um, spend in order to attain a utility level of u of little u of u bar, and in particular it's p, the vector of prices, times the vector of demands, p dot h star. So here are some properties of the expenditure function. E of pu is 1, non-decreasing in p. So if I increase prices, I'm going to have to spend more in order to attain the utility level u bar. Of course, more means could be zero amount more, but more in the weak sense. I can't suddenly spend less because you charged me more for each good. That's impossible. The intuition is clear. 2, it's homogeneous of degree 1. If I double all the prices, you're going to spend twice as much. The only reason why I would change my composition of my bundle is because there's different trade-offs, right? Remember, the marginal rate of substitution has to equal the ratio of prices. If I double all of my prices, I'm keeping the ratio of prices the same. The trade-off between x and y has remained intact, and therefore I'm not going to change my composition of x to y, which means I'm going to end up demanding exactly the same goods. So if I double my prices, the Hicksian demand remains the same, but the price of that Hicksian demand doubles because the expenditure function is just p, which is now 2p, times the same object, the same vector of Hicksian demand. 3, the expenditure function is concave in p. So this bears a little bit of intuition. The idea is that as prices become more extreme, I can go away from the extreme values, right? So if I make p really expensive, I can, if I make px really expensive, the price of x really expensive, I can move towards consumption in y. I can adjust my consumption, which means that I spend more when prices are close together, right? Because then I can't avoid the expensive goods. So if prices are really extreme, so x is really expensive and y is really cheap, I can substitute away from x. If y is really expensive and x is really cheap, I can substitute away from y. If they're both in the middle, I can't do any kind of substitution, and so I have a higher level of consumption expenditure. But it bears maybe drawing a little bit to find a bit more intuition here. So let's just look in one dimension. I mean, we'll draw it in 2 dimensions, but we'll look in 1 dimension. So say that we have our expenditure here, E of P U, and here we have the price of good X, right? So we're just going to, when I say 1 dimension, we're only going to worry about the price of one good at the moment. And say we have some point here, and that's on the line, right? So this is the expenditure, say px, py. So when there's a given, for a fixed py, this is the value of the expenditure function given px. Now say that I make x bigger. If I make x bigger, what I could do is just, what the consumer could do is nothing. They could consume the same bundle, right? So remember that this is equal to P dot H star. So what they could do is they could just continue to consume H star. So they could just consume H star. We know that H star satisfies the utility constraint. H star generates the utility of U bar by definition. I call it U bar, and in the notes I write little u. It generates utility little u. H star does that because it's by definition of being H star. It may no longer be optimal in the sense that it may no longer be the minimum expenditure, but so when we change x. So if we change to px, what we could do is just do nothing, right? So we could say that, what? So if we have this point here, we'll call this the pseudo expenditure function, and it's just the cost of P dot H star of P X P Y. U bar. For a fixed H star, this is just the cost of H star, the same H star, not the new maximized H star. It's the cost of H star, where H star is the optimal bundle at that point for that PX, but at different values of PX. And the slope is just H star times PX, right? It's just how much am I spending on X, right? It's just changing linearly with my change in X. As I decrease X, it just changes at a linear rate according to how much X I'm buying in H star. So, so what do we know about the actual expenditure function? We know that the actual expenditure function must be less than this line, because that is a particular way of generating a value of U bar, right, for any of these PXs. This does generate, this satisfies the constraint, so whatever is the minimum cost way of satisfying the constraint must be less costly than this particular bundle, which means that the expenditure function must be below, what we know is that it's below this line. It's on the graph here, right? And we know that it happens to touch, actually. It touches at the point, by definition, we pick the point to be on the expenditure function, so it touches at that one point, but at every other point, it's in this green region. It's below that line. Now let's pick another point. Say the other point is below the line over here, right? And now we're going to have, this is going to be H prime star, P dot H prime star, or P, let me get out of here a little bit. This point is E of PX prime PY, same PY, but we're choosing a different PX. And the same utility. And we know that it's below that line, the original dotted line, right? We can do that same exercise, and we can find that, maybe there's some other composition, so the slope is different here, but the slope must be something at this point here. And therefore, we know that the expenditure function lies beneath both of these lines. So it's beneath all of these. And you keep doing this, and you'll find that you're creating an upper envelope, right? And if you trace it out, that's your expenditure function. Now remember, way back to the first lectures, one of the definitions of a concave function was a function that lies beneath all of its tangencies. Is a function that lies beneath all of the points of tangency, all of the tangencies that intersect it. So that means that the expenditure function is concave, right? The expenditure function must lie beneath all of those tangent lines, which means that it's, by definition, a concave function. So that's a nice graphical interpretation. The intuition is that when I adjust prices, I could linearly extrapolate. I could do nothing, and my expenditure would move linearly. But I'm allowed to adjust. And so because I'm allowed to adjust, I don't have to stay at a linear rate of progression up or down. I can actually manipulate my balance of X and Y. I can change my bundle, and therefore I can make it cheaper, potentially make it cheaper. It could be linear if I never change my composition. So 4, the expenditure function is continuous. I think that's kind of obvious. If I change prices a little bit, I'm not going to suddenly spend a ton more. And the last one is called Shepard's lemma, and it says that the Hicksian demand is the derivative of the expenditure function with respect to PI, and that is a direct corollary of a general result in optimization theory called the envelope theorem. We can talk about the proof another time, but it's helpful. That's a helpful result to have in our handbook. So the reason I wanted to talk about those particular properties is it allows us to talk about this theorem, which is one of the cornerstones of the whole class. It's called the law of compensated demand, and it says when a price increases, Hicksian or compensated demand decreases. So dH star I, dP, I think this should be a weak inequality, not a strict inequality, but dH star DI, dH star dPi is negative, is less than 0. This does not hold for Walrasian demand. So this is, I want to actually, um, I'm going to really quickly change that to a less than or equal because it's going to bother me and I think it's wrong and I don't want anyone to think that it might be that. So I'm changing it, but you can't tell because I'm on the window thingy. But there it is with the inequality. So when a price changes, the compensated demand decreases. What's going on here? And this is important because it's important because it has a great intuition, right? When prices increase, I want less of that good. I'm going to substitute away to other goods that are cheaper. You make apples more expensive, I'm going to buy pears instead. You make T-shirts more expensive, I'm going to buy button-down shirts instead, whatever. I'm going to substitute away from goods that are expensive, which means that I don't like increases. I mean, demand is downward sloping, right? You always think about supply and demand curve. This is the result that says demand is downward sloping. But it's not saying that Walrasian demand is downward sloping, which is really what we think of when we think of downward sloping demand. We're thinking about how much does a consumer buy according to a budget, not how much do they buy to keep some utility level constant. The result that we have in our model is that compensated demand is decreasing, not that Walrasian demand is decreasing. So this is very subtle and very important. Walrasian demand is not downward sloping. In most cases it will be, but we can't guarantee it. The model does not force it to be downward sloping. The model forces Hicksian demand, compensated demand, to be downward sloping. The intuition is exactly what I said. When goods are cheaper, you want more of them. When they become expensive, you're going to substitute away and buy some other thing. You'll never buy more of it because it became more expensive. This is not true for Walrasian demand for a very interesting and subtle reason, which we're going to go over in a class or two. So if you think of just skirting that issue, that'll come up. We'll come back to that. Here's the proof. So from the prior theorem, we have that the Hicksian demand is the derivative of E with respect to P. So dE dPi. So dH dPi is the second derivative of E with respect to P. The second derivative of the expenditure function with respect to the price of good I. From that theorem, E was concave. A concave function has a negative second derivative, right? A concave function has a negative second derivative means that dH dPi equals d squared di dP squared is less than 0, less than or equal to 0. So, so that's the proof. That's a really nice, we did all the work already on the other theorem, and now this one just falls out, and that's a pretty beautiful result. If you're not impressed with this slide, man, watch the video again. You're going to like it. The second time through, I promise. I think that's all we got on this. We're going to return to these notions of Hicksian demand, Walrasian demand, the relationship between the two of them, and this downward sloping business in our next lecture on comparative statics and how prices influence these demands.